Learning calculus the way it evolved is generally a lot easier and much more intuitive than the way it is currently taught. And this will be the topic of this series, the history of calculus. But first, we want to develop a general understanding of calculus. That is, what is calculus? Why do we need it? And how does it work? And this will be the topic of this video, calculus in a nutshell. So let's start with the first question. What is calculus? Calculus originated as a tool to analyze and find properties of different mathematical curves. Let's take this curve as an example. Calculus helps us find many of its properties, and I'll talk about 5 of those. The first property that calculus helps us find is the area under the curve. Historically, this was known as squaring the curve, or finding a square with an equivalent area. It was mathematicians' quest to square different curves that led to the discovery of calculus. The second property that calculus helps us find is the length of the curve. This was known historically as rectifying the curve, or finding a straight line with an equivalent length. The third property that calculus helps us find is the concavity of the curve. Is it bent downwards? Is it bent upwards? Is it just a straight line? And if you're wondering, but isn't it obvious to which way the curve is bent? Remember that these curves are usually given in an equation format, and their concavities are not immediately obvious. The fourth property that calculus helps us find is the tangent to the curve. Historically, the tangent was defined as the line that touches the curve at one point only. This definition has been modified since then, but to keep things simple, we will stick with it for the time being. Together with squaring curves, finding tangents was a major catalyst in the discovery of calculus. And the fifth property that calculus helps us find is the point of maxima, or the highest point of the curve. And if the curve is bent downwards, then the point of minima, or the lowest point of the curve. I like to think of calculus as a machine with a dial. We feed in the curve we want to study, set the dial to the property we want to get, and it gives us the answer. Over the years, calculus evolved from analyzing curves into analyzing functions, which are more generic and abstract mathematical objects. But since curves are more visual, and since they were the objects that were being studied when calculus was discovered, we will focus on them for now. The second question is why? Why were mathematicians interested in analyzing curves to start off with? Now, in general, mathematicians are interested in mathematics for intellectual purposes. They are driven by a sense of intellectual challenge, intellectual beauty, regardless whether or not their work has any practical applications. But in the case of calculus, there was also a major practical motivation. See, it was discovered that many, if not all, measurable phenomena in the universe could be represented by curves. So, for example, the speed of a pendulum can be represented by this curve. The distance covered by a falling object can be represented by this curve. The growth of bacteria in an enclosed environment can be represented by this curve. And the list goes on. So when we have a tool like calculus that can analyze and find properties of different curves, we have a tool that can analyze and find properties of different phenomena in the universe. And this was a major motivation for analyzing curves and subsequently discovering calculus, and a major reason why calculus today is considered one of the most important branches in mathematics. The third question is how? How does calculus work? What's happening under the hood of our machine? Calculus uses two simple processes, cutting and stitching. For example, when we want to find the area of the region under the curve, calculus cuts the region into infinitely small pieces, find the area, or more accurately, the equation of the area of these pieces, and then stitch them back together to get the total area. Similarly, when we want to find the length of the curve, calculus cuts the curve into infinitely small pieces, find the equation of the length of these pieces, and then stitch them back together to get the total length. For some properties, we only need the cutting process without the stitching. For example, when we want to find the tangent to the curve at a particular point, we use calculus to cut the curve into infinitely small pieces, and then extend the piece at that point to get the tangent. And when we want to find the point of maxima, we use calculus to cut the curve into infinitely small pieces, and then look for the piece which is horizontal, and that would be the point of maxima. And if the curve is bent downwards, then that would be the point of minima. Calculus branch that deals with cutting is called differential calculus, and its branch that deals with stitching is called integral calculus, where we integrate the pieces back together to form a whole. But now we want to address a vagueness in our terminology. What do we mean by an infinitely small piece, or what is known as the infinitesimal? Is it bigger than 0? If so, can't we just cut it in half and get a smaller piece? And then cut that piece in half and get even a smaller one, and keep doing so indefinitely? Is it equal to 0? If so, isn't stitching zeros together results in nothing but 0? Pioneers of calculus in the 17th and the 18th century were aware of this vague and illogical nature of infinitesimals, but they couldn't resist using them as they gave correct results. It wasn't until the 19th century that mathematicians tackled the problem of infinitesimals. And to do so, they eliminated infinitesimals altogether, and they introduced limits instead. And while they succeeded in putting calculus on stronger logical foundation, they also made it much more difficult to understand. And this ended up being the curriculums that we currently study around the world. But it is a lot easier to follow the natural evolution of calculus. So for the time being, we're going to adopt the attitude of the pioneers of calculus and pretend that we can indeed cut something into infinitely small pieces and then stitch them back together to get different results. This method of solving problems by cutting and stitching predates calculus by thousands of years. Ancient mathematicians used it to find areas and volumes of different shapes. But the main difference between calculus and its predecessors is that calculus makes this process of cutting and stitching systematic. See, with earlier methods, different shapes needed to be cut and stitched back differently, and this usually required a lot of ingenuity and creativity. For example, Archimedes, one of the best mathematicians of all time, used this cutting and stitching method to find the volume of the sphere. He worked out that the volume of the sphere is 2/3 the volume of the cylinder that surrounds it. He was so proud of this discovery that he asked for it to be engraved on his tombstone. Today, with calculus, a school student can find areas, volumes, and many more properties of shapes and curves that Archimedes didn't even know existed, let alone be able to find their properties. And such is the power of calculus. It reduces problems that once required an Archimedes into a set of rules and symbols that anyone can apply. And this is calculus in a nutshell. It's a systematic way of cutting and stitching to analyze different curves and functions, and in turn analyze different phenomena in the universe. So let's go back to where it all started. Ancient Egypt. See you in the next video.